Hi, today I'll be talking about planning with online topological memory. This work is done in collaboration with Sam Powers, Victoria Dean, and Abhinav Gupta. To provide the motivation behind this work, currently model-free reinforcement learning algorithms fail to reason effectively over long horizons. To address this, recent work in simulated visual navigation has combined RL with planning by constructing a graph on observations. So on the right, we show an example of visual planning from search on the replay buffer. So search on the replay buffer uses graph search to find visual waypoints for a policy to navigate with. Their method builds off of prior work from a paper titled Semi-Parametric Topological Memory. So the general algorithm is that a task goal is localized as a node in the graph. Graph search is done to find a path, and then these subgoals or waypoints are given to the local policy. However, these methods build a graph offline, so planning cannot be done while training the goal condition policy. Subsequently, these methods are difficult to apply to tasks that require more complex policies, such as manipulation. To this end, we introduce online topological memory. So our method constructs a graph on observations online and plans subgoals using the graph while training the policy to guide exploration and induce a sort of curriculum wherein the policy must reach subgoals planned before attempting the final task goal. Here we also show some diagrams of our method. So given an incoming trajectory, we perform a graph update by associating states in the trajectory with nodes in the graph and merging nodes that are within some neighborhood of each other. On the bottom, we give an example of planning for exploration. So if the task goal cannot be localized in the graph, then our method selects a random node to explore to. The policy returns the states it has already visited and then begins exploration. If the task goal is achieved, then a node is added to the graph. Note that the task goal is a longer horizon goal, so it would be difficult for the agent to reach if it was just doing random exploration from the starting point. So we perform evaluations to answer the following questions. Number one, does online topological memory help long horizon reasoning? To answer this, we evaluate in 4 rooms point M, where an agent must navigate from the bottom left to a top right room. This is a long horizon task, as over 100 time steps are needed to navigate to the task goal. We also perform an evaluation to test whether a method can handle tasks with different goals using fetch-push, a manipulation task where a robot must push a block to some position on a table. While unlike forums point M, fetch-push is not a long horizon task, these tasks both use difficult sparse reward functions, where the agent receives a reward of 0 if it has achieved the task goal and -1 otherwise. So our method is plotted as the red line, and these results show that our method can solve this long horizon goal-reaching task and is more sample efficient at learning than the RL baselines. We also conduct further analysis on the forum's point M results. So how does planning subgoals guide the goal condition policy? Here we visualize trajectories taken by our method with and without planning subgoals. Only by planning subgoals is the agent able to reach the final task goal. On the right, we also show the corresponding graph used for planning. The cyan nodes are the exploration nodes, and the orange nodes are the subgoals used in successful trajectories. Next, we evaluate whether planning results in efficient exploration. Our method is the leftmost one shown. Note that our agent consistently visits parts of the environment relevant for achieving the task goal. For future work, we plan on learning a neighborhood function online for image observations. Currently, we use the L2 distance between state inputs. We also hope to evaluate on more challenging multi-step continuous control tasks with image observations. I want to thank my collaborators and the sponsors of the RISC program for making this work possible. Thank you very much.